Yeah. Flore, tu veux faire une introduction pour la deuxième partie ou je commence ou comme tu veux?
Rapide.
Super.
So welcome back to the second part of our colloquium. So we are now on the part where we are going to discuss how we're going to move tomorrow. And so we are much more projecting our perspectives this afternoon. And we're going to start with Jacques' presentation. So the floor is yours. Thank you.
Thank you. So I know I have the luck to be directly after lunch, so I hope you will not fall into your nap time, but will stay awake a bit. We're a bit late, so I'll speak even quicker than I do normally, but I hope, no, I'll do my best. So what I want to talk about is future uncertainties in mobility solution design. And what we are working on is a scenario-based design support framework. I'm going to talk a little bit about what that is later. My name is Jacques Gall. I'm a PhD student here at IRT, at LGI, the Laboratoire Génie Industriel at Centrale Supélec. And at my heart, I always stay an urbanist. So you will see a couple of references to the spatial dimension of things because it's the background for me. I'm going to talk about three different parts. First, a bit the context and the motivation, what we are working on, the contributions or some of the contributions so far, and the methodologies we are applying, and then talk a little bit, at least briefly, about the practical application which we are working on. To start with, the context is, I started in October 2020 at the Anthropolis chair. I'm supervised by Bernard Yanou from the Laboratoire Génie Industriel, Flore Vallée, who you have already heard, and Sylvie, who has been already very active already this morning as well, who is a senior researcher at ÖDF. So we have a bit the different disciplines, and generally we are at an interdisciplinary perspective, a bit with design science, urban studies, complex system engineering, and everything what's somehow related to mobility, transportation, and so on. And we have two different application areas. One is the metropolitan Paris area, but more in particular, the Communauté de Paris-Saclay, so the yellow part here. And then there's a second case study where I'm going to talk a little bit about later. You see our partners, but we had the introduction already earlier. And very general, I think there's no need to repeat that, but there are different, very global challenges which are connected to mobility. So of course, everything related to the environment, greenhouse gas emission, also noise, the resource constraints, and so on. There's a socio-spatial justice element. I think we got a very nice presentation from Widat about it earlier. So the different stakes there, but also the economy. So for example, there's a huge amount of money lost every year in the Greater Paris area through, now I'm mixing in French and my English is even worse. The economic stress which can be put on the inefficiencies of the mobility system. And to summarize a little bit, we also refer to the SDG 11.2, which asks for the safe, affordable, accessible, and sustainable transport systems until 2030, which are accessible to all. So there's also the inclusivity part integrated. But that's a global part. On the other side, we have a very strong local diversity. So most of you probably know the image on the left. That's the Rue de Rivoli in Paris, which has been transformed a lot at the beginning of COVID. In the middle, you have, I think, a quite beautiful photo from the Saclay Plateau, where you see the construction of the Metro 18. For at least the ones who are here have seen it this morning. One of the biggest infrastructure projects at the moment. We are currently somewhere back here. Already, these are completely different, despite that many people are using both of them on the same day. And then, again, I will talk a bit more about it later. There's Cairo, which is one of the biggest metropolitan areas in the world, where you have incredibly high density, where you have completely different mobility offers, challenges, and socio-economic system. So all of them have their particularities, and we try to not, even if we're working with very particular cases, we are trying to find ways which can be applied to different contexts. That's one part of the complexity. Another one is the time. So we talked already about perspective a little bit in the morning and the temporal dimension. And here you see different, so some of them I think you saw earlier in Julien's presentation, the different documents, the different policies and so on, which exist and their timeframes. So when were they published and until when do they refer in the documents? You see there's a strong variety between the different scales. But also, and that doesn't go only for policies, but also for products and services, many of the solutions are created, or let's say we have an idea today. you solve mobility after this great colloquium in the evening, and you're like, okay, this is what I want to do. It will take 6, 7, 8 years, depending on what sector it is, until the solution is actually implemented. And then you want the solution maybe to last for another 10 years or 15 years or possibly longer. So there are a lot of temporal issues. And the question which we are asking, if we are really prepared for the context and the needs of tomorrow, because whatever we do today has an impact on, well, how people will move or how people will act, for example, in 15 years from now. And this is a bit the answer. So I think we don't. This is a graphic from a book from Robert Goodspeed, who's working a lot with scenario planning in the urban context. And this is the city of Dresden in Germany. And he looked at all the different documents over a long period of time, what population development they assumed and what the reality was. So this was always the assumptions, and the dark black line was the reality. So the only thing which was consistent was that they're always wrong. Nearly, there's one, this one is not that bad. But it's super hard. Also, Dresden is a very particular case because, well, it's a small detail, but anyway, we don't really know what's happening. And every time when we make an assumption, it's very likely that we're proven wrong. And this is the only thing which I think is quite coherent about the past. Or as said by Hermann Kahn, one of the early futurists, the most likely future isn't. This brings us to the point of departure, which is we have complex challenges across different dimensions, and we have an urgent need to design solutions which are adequate in order to solve at least some of these issues, which, however, work both with the local diversity and uncertain futures. The goal is thus to work on a design and decision support tool, which does a couple of different things. And the research question which we formulated based on this is how we can support the design processes. And design process is not product design or service design, but also policy design. So it's a bit in the different dimensions. Second part is about some of the early contributions. So as I said, it's the end of the second year, early of the third year. So we have already done a bit, I hope. There's still some time left and quite a lot of things to do. So I want to talk a bit what we did so far and also what methodologies we are using for the application cases, which I'm going to talk about afterwards. The first one is we see urban mobility as a complex system or a complex adaptive system. So we had a conversation earlier at the coffee break about what is mobility, transport, and so on, which is a very recurrent conversation. So what is part of the urban mobility system? Is it just the metro system? Is it just something, or is it a combination of a lot of different things? And we are trying to see it in a way where, for example, people are also integrated. It relates a lot to the presentation from Flor earlier on the infrastructure, but it also includes the digital systems, and includes the energy sector, of course. It includes a lot of different parts which are connected. And we organized it a bit based on interviews and literature on primarily 3 different layers. So the layer of people, which includes behaviors, practices, preferences, and so on, the mobility service, and the infrastructures. That's the first part. The second part is the simulation of alternative futures or scenarios, or the scenarios, let's say, the way we use in order to do so, through the integration of trends and uncertainties. And the last part is assessing these different alternatives and using them for some kind of strategic insight. I'm going to talk primarily now about the second part. And here we are going back to our personas, our family, which you already met before. So earlier you were in the year 2022, now you're, let's say, 2030, 2035. And Mathieu, the child of the family at that point, will have a job or will have to go to work in some way or the other. And the question is, depending on the context, even if he lives always at the exact same place, if it's a very high dense environment with a good infrastructure, he might take the bike. If it's a very techno-driven environment, he might take the autonomous shuttle. Or if we are completely in the teleworking mode, he will sit at home and not go to the office at all. So this is just, it's a very, very restricted visualization, let's say, of the diversity, but these changes of behaviors, of choices, make a very significant difference on how we have to plan the mobility systems for tomorrow. If we visualize it a bit different, this is one of the earlier works which we tried to do. So we took a futures cone, which is used a lot in the futures field, and try to adapt it a little bit to our needs. So we are currently here, and as further we go into the future, as more different possibilities are there. And then what you see in the end are different scenarios. So theoretically, they're infinite scenarios, but it doesn't make sense to work with infinite scenarios. So normally there's a number, let's say, between 3 and 4, 5, 6 maximum. And then they're distinct. We distinguish between them, for example, if they're probable or plausible or possible, if they're preferred, in case they're preferred by whom, on what basis. So this is, let's say, a little bit the conceptual framing of it. But then the question is, what are these lines in between? Because this is the possible pathway which we are going through. And we want to understand what impacts this transition pathway, or what allows us to try to understand a bit how it works. For that, we focus primarily on two things, trends and uncertainties. Also there, Julien had already the question on what trends we know, or we really know of, and how we can quantify them somehow, but also how we can assure that they will continue after COVID. I think you gave the perfect response to it, because we don't really know what's happening. We can make some assumptions on it. And then on the second level, we have the uncertainties. So these are really the things which we have no clue about, because not no clue, but don't have a lot of ideas about, because it can go in many different directions. Trends, defined as anticipated future development with high level of certainty that is assumed to hold true for all different future scenarios, are, for example, population growth. So it's very unlikely that we have a decrease in population in the next 60, 70 years, depending on the country. If you talk about France, it will be quicker. We will have an aging society, primarily again in the national context. And the Metro 18 is relatively probable, because we can see it coming every day a little bit more. So those are trends, and we can integrate them into our planning today. On the other side, we have uncertainties, and there's a lot of speculation, depending on who you ask, what people you work with. If you work with people from IRT, then the uncertainties are, or the assumption on uncertainties is very different than if you work with urban planners, for example, because we have very different assumptions on what people do, how people will behave, what you want. And one big factor in mobility, of course, is the individual car ownership. So Mariana also has been talking about that. User preferences in general, why do we do the choices, on what basis? But also the spatial part. So how is our urban environment going to look like? Do we have to go very far? I think many of you know the concept of the 50-minute city, which was very much promoted, or is very much promoted in Paris. So all of these are elements which we don't know in which direction it's going to develop. We can hope, we can say we would like it to go in this direction without necessarily knowing what the impacts are, but it's uncertainties. So we have many trends and many uncertainties, which means we have a million of different scenarios, which is probably the case, but it doesn't help us a lot. So what we are trying to do in order to reduce this complexity is exactly using the scenarios and simplify them. And there's a very nice approach developed earlier by Jim Dater, later developed in other fields, and recently from Niszkolski applied to the mobility context. So he made a very large literature review on all the different scenarios you can find in urban mobility until 2030. And he categorized them, maybe not with the best names, but grumpy old transport, which says things stay as they are. At an easy pace, we transition, but not very fast. Mine is yours. That's the scenario of Mariana with the mobility as a service. So you share more or less everything. And then tech-eager mobility, which is really autonomous shuttles, everything, every way we can use technology. This is the general part. Now it's the local adaptation. So how can we adapt this to the local context? And there I come back to the system or the complex system definition. So we have the people, we have the services, and we have the infrastructures. They are, of course, all interconnected in a million different ways. But what we are trying to see a little bit is the order of the connections between them. So what impacts what, and which change in one of them affects how the other layers. And what we are trying to do a little bit is to say, well, the population development is what comes first. They define the demands for the mobility services. They define where development takes place. But at the same time, the infrastructure, so the built environment, I think, Claude, you made the reference to the no further land grabbing or no further artificialization. So there are constraints coming from different parts. But generally, there's a bit of an order and a bit of an interaction between all of them. This we translated a bit into a framework, I guess, more or less, at least a colorful graphic, which tries to explain a bit the different ideas. So we have the different layers and the different scenarios, which in this case are the ones which I showed before, but they can also be very different ones. And then the question is, if we want to know the contextual scenarios which are possible for 2030 or 2040, how can we adapt each of the different layers in order to, well, work with it and see if a mobility service, for example, works. First one would be the people. So what are the demographic developments? Again, trends, uncertainties. The next one, the infrastructure. How does the built environment react to it or has to react to it? And then the service layer. Afterwards, assessment and visualization. This as a framing, let's say, from a methodological part. Now the application, as I mentioned, we work primarily here in Paris-Saclay. And now very soon, meaning next Monday, we're going to add a second case study, which is in collaboration with the American University in Cairo and the transport agencies there to have a little bit of a diverse context. So we have two application cases here and another one in Cairo. However, with a very similar context as here, where you have a long or a very dominant public transportation intervention and the idea to transform the behaviors of people. I want to talk about the first one, which is a bit of a future-proofness, even if I don't like the word, because it says that we can prove something for the future, which we cannot, but the attempt to do that for a certain mobility solution. And again, the first layer is people. So what differences can we see in people's behaviors, on people's characteristics, their socioeconomic characteristics, their preferences, where they live and so on, for different scenarios, such as these. For that, we are using two different parts. Personas, Flor has been working on the chair and Flor has been working on it for a long time. Personas are, let's say, archetypical descriptions of people. And at the same time, we're trying to link it to static populations or, let's say, any kind of more quantitative approaches to working with the human dimension. And we do that by trying to cluster existing people and redistribute the clusters for different scenarios to see how we can integrate them in both qualitative and quantitative design process. And just to give a very brief overview, here we work with all the Ile-de-France region, even if we only care about the mobility within, because people come from outside. And we did different clustering methods in order to define a number of clusters, took the information from that. I don't want to get too much into detail, but that results then afterwards in personas, which are a little bit like the characters for our presentation. So for example, the cluster number 9, which we have at the moment, is an unemployed married mother of 1 child, born abroad, living in a 3-room, 60 to 80 square meter social housing, blah, blah, blah. So this is the level of detail of variation of humans today, which we can see how they're distributed in different areas and in different age groups throughout the Ile-de-France region. And then that's the interesting part, is the integration of the trends and the uncertainties. It's trying to adapt how we can integrate demographic changes, overall growth, but also uncertainties such as changing preferences into the process. And for that, what we are doing more is we're trying to redistribute the personas, or we are trying to redistribute the different individuals according to our different assumptions coming from literature and interviews throughout different scenarios, to have a different constellation of the population, which then, in the other way around, can inform both qualitative design process through having scenario, a contextual scenario and a persona, but also can, for example, inform the generation of synthetic populations of different future scenarios. And yeah, this is more or less just a way back. So taking also the information from the quantitative part to inform the qualitative elements. I think I'm already talking too long, so no, it's okay. I will anyway try to hurry up a bit. This is the first part. I was just really, really brief on it, but the idea is more or less to combine different qualitative and quantitative elements, spread them about through different scenarios in order to see in different possible futures, how would a certain solution, for example, function or not function. Second part is the infrastructures. It's a beautiful sketch, not as nice as the other ones, which we got, but a bit simplified. But the idea is the spatial environment. If we have a very strong population growth in one particular place, how does the urban environment has to adapt to it? Here outside, you see a very good example, because very few years ago, there wasn't much. Now you have already quite a somehow urban area. And depending on how the development of the plateau continues, it will either be completely densified at some point, or it might stagnate at some point. So this has a significant impact on where, for example, trips start, what services are needed, what the questions of accessibility and so on contain. And then finally, there is the third dimension, which is the mobility service, which is of course the end goal of the whole process. And this is the question, what mobility service how would current mobility services work within these different contexts in, for example, 2030, but also how can a potential future mobility service serve this context? And how can we make sure that it is robust across different scenarios? And this is what Tarek is going to talk about in about half an hour from now, I think. So there's questions on the integration of different modes. There's questions on fleet sizing and so on. To again, vary on a quantitative and precise size, how that could be integrated. And that brings me to the conclusion, which is that what we are trying to do is get to people-centered and sustainable mobility futures by considering trends and uncertainties in the process. We do this through a scenario-based design approach, which is using a lot of methodologies which exist already, but extending and adapting them to our context, integrating, for example, the localization part. And we try to use as many simplifying elements as possible, such as archetypes, personas, and so on, because it makes all of these things much more tangible and on the one side, possible to work with people who don't work with large or with big data or whatever. So we have a qualitative approach in order to work with it. On the other side, it's also a way to work with the future because we have no clue what's going to happen. But the simplification allows us to categorize a little bit different trends and try to see how they might look in order to see the possible reaction to our mobility service changes and so on. And the next steps are the continuation of the two application cases here, as well as the replication in a very diverse but also very critical context where a lot of the mobility changes or challenges today already exist, much more so in the future, which is going to be in Cairo or New Cairo more precisely. Thank you very much.
Thank you very much, John. Any questions in the room?
Yes. Yes, Jack. One question I've seen somewhere in the slide, the term quality insurance. Does it refer to the fact that maybe you can set up some kind of management tool that will support some adjustments or I don't know, a reflection towards the integration of the best way during the time, the evolving time. That's the idea.
Thank you for the question. If I would have told you a question before to ask, it would have been that one probably. So I will try to repeat it. The question was on the quality assurance. Was it in this slide or was it? Yeah. So it's about the assessment part, but the different dimensions of the assessment and how or what the goal is behind it. If it is the goal to, for example, ensure that we can, well, somehow accurately represent the pathway, or
yes, but there's also the dynamic dimension. I don't know if it's included in your approach, but yes, I don't remember all the other.
So throughout the time, so that you can, yes. So the impact assessment or the assessment part has a bit of different dimensions. One of them is a bit related also to what Julian was presenting earlier. So it's really the impacts, the economic and impact assessment and so on. The other one is impact evaluation, which is if people work with futures, what happens to their way to work with it? So how does it change how does it transform their way of working? And the other one is the quality assurance or the how to say it, Flora, please intervene when I say something which is wrong. But it's
on the scenarios actually.
It's trying to find out how the scenarios need to be in order to be valid and useful. So what are the characteristics? And then that also becomes over time very interesting because you can see, well, did it fulfill the role it was supposed to fulfill? Is it accurate? Does it somehow fit? Can we readapt them? So also we don't see it as a, say if we would do it in an exercise for 2040, it wouldn't be a single exercise today, but it would have to be some kind of a, maybe to take my favorite ice cone. Every time we move one step here, we have to adapt because it's going to be different possibilities from there. So it's like a moving cone which comes with it, and it would have to be reevaluated. And then every time see, oh, well, I think this is also a way how we can improve our accuracy, even if it's very difficult, because even in the past, we know that it's very difficult to be accurate.
And if you have a look at the paper, you have 12 or 13 cones.
Yes, there are a lot of cones.
If you are keen on cones.
Can we
say so.
Codes I think.
Yes, it's a very dangerous field.
Any other questions?
François?
If you come back on the slide, maybe it's too soon, but what do you put in the scenario visualization?
Very good question. I like your questions today. So we talked about it from time to time, but not in a very precise way, because it wasn't the most important part yet. But in the end, in order to make it tangible, and that goes again to the fact that it should be a tool for people to use, it needs to be usable by people. And there are different parts. So here, written, probably not possible to be seen by everyone. There are personas, media, and stories. So personas are our way to transform human stories or people characteristics into something tangible. And their visualization, it doesn't just mean visualization as images, but also text and so on. So you have a person, a bit like, I don't want to go to the other slide, but you have a photo, you have a name, you have a characteristic, you have a bit of a story behind it, which makes it, and I think that it's been used for quite a long time. Since 2003 by Microsoft, they started to use it for all their products to really, well, you know very well that as well. But it's one part on that visualization. On the scenario, it becomes a bit more tricky. So they're normally always stories around the scenario as well. You can visualize them. They're very artistic approaches where it's very abstract art nearly, and there are other ones which are really precise visualization. So I think it depends a lot on what you want to do. And in our case, I think the story part, the people part is one very important element. The other one is the space. So through maps, through development, or through platforms, for example, where you can see the development density change in different areas. That's one way where also in planning scenarios, it's used to really show not where a building will be, but where more people will live, for example.
I understand that in your final methodology at the end of the PhD, you will go and sit there, providing some tools and some steps to.
I hope so. Yes. So I'll repeat again. The question is if I try to go there. So the focus currently lies on the colored ones, but we cannot really get to the end of a tool without integrating at least a part of this. So even if it's maybe not the most important part, and we probably more rely on existing work, but it needs to be there in order to make it tangible to work with them.
Are there any questions online? Or?
Yes.
Have you talked about remediation techniques, communication or tech available?
Could you rephrase the question just that I'm sure that I understand it correctly?
For the remediation, when you are on the code and you have to change the way people act.
Okay, so about the transformative part, let's say, where you try to change, you see this might be a possible pathway, but we want to change it in one way or the other. Yes, well, in the end, this is of course a goal. It's not just a goal to see what could happen. It's one way to apply it today to say what could happen and what might work in the future. But the interesting part is, of course, where you could say, for that, I will go back to the other slide. I find it. So now this shows the whole timeline, but then there's this area of preferred future. And this is, it's very hard to define. There's assessment part again, what is preferred, for whom is it preferred? Because people have very different preferred futures. But there's a very important part, which is the backward influence of futures, or the backcasting as it's called. So the opposite of backcasting, forecasting, where you look at what actions do you have to perform today, tomorrow, and 5 years in order to get to a certain future. So this is not adapting while you're on one, but this is, let's say, preparing to get into a certain direction. But there are many other tools which are really in the transformative part, which I think we worked more on in the beginning, but at some point we were like, okay, let's focus primarily at preparing or supporting decisions done today, which should inform in one direction or the other in which direction we move, but a little bit less on really the different transition dynamics which happen along the way, even if they are very close, both very close connected. So it's, and then on the technical side, futures studies is a very broad field. So uncertainties is a topic which applies in many, many different places. I think we have a very typical approach for certain fields, for the future studies field, but there are incredibly many interlinkages to any kind of technical intervention at different stages. But we try to, I think, not have it in the broader level, but for example, in the modeling of population dynamics. So what tools exist where we can see what kind of different trends can be integrated and so on. So I think the technology part would be, but again, feel free to say something different. But I think the technology part is there as a supporting tool to integrate uncertainty into subparts of the overall framework.
Could you say a little word on what you're going to do in Cairo? Just a little bit.
Yes, I will. Marina, you want to ask your question first?
Just regarding how you plan to give the parameters of what a good scenario is, and what you know already what a good scenario is, how to choose uncertainties to validate as a next step towards scenarios.
Yep. So this goes again to the quality assurance of working with scenarios. For example, I talked a bit about the number of scenarios. And if you have 2 scenarios, it's like one against the other. If you have 3, it's the one in the middle and you have the 2 competing. So you don't want 1, you don't want 2, you don't want 3. But 4, for example, is a good number because you have a bit of a range. So there are certain very simple ways. And then if you have more than 7, 8, 9, it becomes too complicated. So this is on the numbers, for example, one part. On the trends and uncertainties, it's really about finding the most important ones and trying to simplify it to something which we can manage. And for this, we are using the archetypical scenarios because it allows us to choose from a lot of different uncertainties, focus on some of them and translate them into something, even in some cases numeric, which is more tangible than other things. So I think it's in many cases, it's a choice. It's a bit of experience from literature, and it's also a bit the experience which we have from the workshops and so on, where we saw that certain things worked and other things didn't work. So it's a bit of a learning process to see what the idea is. I think a bit to have a checklist on if you want to work with a scenario, what boxes do you have to check in order to fulfill the requirements of a process like that.
That's one of the deliverable of your PhD. That's one of them.
Yep.
It's, I think, very valuable.
Then I think
maybe we have to move on. If you want to say just 2 words on what you're going to do in Cairo.
Yes, I'm going to be there for 2 months in a collaboration between here and the American University and Transport for Cairo, which is an organization working with a lot of informal transportation as well. And we are looking at one of the monorail developments, which is a big development going all the way from the east to the west and connecting some of the new satellite cities, which are existing slowly around Cairo. So New Cairo in the future, the new capital, and the city of the 6th of October on the other side, and trying to understand what different possible scenarios are there after the monorail has been built. So what changes are possible, focusing primarily on the people's behaviors and preferences. So there's one part trying to understand the behaviors as much as possible as they're there today and the possible impact on the future. And another part there's also very strong. So there's the urban planning, urban development department, with whom we are collaborating, is how the spatial setup can possibly be adapted or might possibly change in the future to make certain modal choices more interesting. So in very simple terms, where do you need a street for people to walk? How does the street need to look like in order to get to the monorail, to take the public transport, to go somewhere instead of a car? That's the idea. I can report back in 2 months. There's one question online, but I think we're a bit. Ma, if you want, you can write it and I will respond in the chat. Because I think we're a bit.
I think we are running a bit late. Thank you very much, Joe. Right, the floor is yours. It's your, no, it's not. It's Michele, sorry.
Ouais, c'est ça. Ouais, là. F5 ou
Non, c'est bon. Voilà. Okay. Good afternoon. I'm Michele Chirico, postdoc.
We will be back in a second.
And now?
Yes.
Yeah. Sorry for the technical problem, and we are back online.
It's okay. Okay. So, so I want to start with Selma. She is 29 years old. She loves do sport and she like a lot also the bike. So she take bike in the weekend, and she also want to take bike every day for his community trip. But the problem is about the infrastructure. She thinks that infrastructure are quite unsafe because there aren't a dedicated line for bicycle between his home to his work. So the point is, in which manner can improve the quality of the trip of this person that now she must take the car, she cannot take the bike. If we change something in the infrastructure, and on the other side, if you change the infrastructure, what is the impact of the people? There are more and more people that will change or not. We are not sure if you change that. So the point does work. Okay. So, so in this presentation, I will show you how we can try to investigate the relationship between the urban form, so for the building and the transportation network, and the mobility mode, and more important, the new form of mobility, and what is this what is this relationship, and also how we can model that. So. I will start with introduce yourself on this topic. In the first step, in the second step, I will talk a bit about around the existing database and how we can create a consistent database to investigate those kind of problems. In the third part, I will show you how we can model it, this interrelationship. I will conclude that. So before to start that, I will refer you, before Jacob say you also, that I'm in the Future Cities Lab. Future Cities Lab is a joint laboratory between the French and Chinese university. And they have different challenges. One of them is investigated the planning, is focus, different focus. One of them is the transportation. And the research is focused also in the framework, in the proposing new framework to modeling also the planning and the transportation. So that is the big framework of this work. Basically, you have a city. In the city, we have a physical element that are also called the urban form. That is the infrastructure and the build, and we have people that move over this space and also interact each other. So the point is what is the relationship between urban form and the way that people behave. And in order to investigate that, I will just propose you a very sample example that we take here two screenshots of Paris, one in 1916, another one is 2020. And we just see what, very basically that you have some transformation. Those transformations are around the different aspects. Around their build-up, it's clear, but one of them is most important is around the infrastructure. So you can see new bridge, you can see new. It's not too easy to see, but you can also investigate that there are a lot of replanning of bus line, for example. We have also the new subway that you created. So you have a lot of transformation just in this area. And also we see that this transformation is driven by new form of mobility that we created. For example, if you see in the last century, you see the great revolution from the animal motored powered transportation that come and also a lot of active transportation mode that go to private and motorized vehicle. And when we see that in the most of these parties around and after the Second World War, we saw also that the infrastructure changed a lot. We see the increment of the capacity, the increase of the capacity of the street. So that means more line of the street, for example. We see the motorway, for example. You never see that before. So infrastructure have a strong new form of mobility, a strong impact to the form of the city. And we suggest that we have to investigate those interrelationship in order to investigate the real mechanism behind the transformation of the city. So before to investigate that, we have to look in front of the data that we have. And in the case of is not enough for our proposals, maybe you have to improve that then. And we just have another sample example. We see Paris, we see Arc de Triomphe, and we see here that if you consider all the data set that we have now, so of the 2022, and we see that there are a lot of inconsistencies. For example, you see that an overlapping of different network, and often those overlapping are not exactly from geographical point of view, not exactly coherent. So you have some distance that create a lot of problem, especially when you have to stimulate those transformations. Also, we see that those databases are in different formats, and those not all formats are compatible with the framework for simulation. So we have those kind of problems. And also we see that there are some information that are not integrated, but we think is very important. For example, just the physical constraint like the width of a street. It is crucial to know that in order to say which kind of mobility mode is possible in this street. Just consider the width, for example. And this information often you don't have in this kind of database. So before to try to investigate it and try to model how it can transform during the time, you have to fix the data. And that is the work that he done in G in last month. So you need we have to have an approach that is focused clearly on the network. And we prefer to consider open access software and open access data too, because in this manner, this is the only manner that allows us to investigate the whole city in the world. So, so our goal is create a very general procedure to apply in different contexts. We have to improve all information that you don't need, like physical constraint. We also think that it's very important to integrate it with some basically transportation and graph analysis in order to better understand this kind of a network and their characteristics. And also, it's very important to consider the locally what will happen, because why that? Because when you have some characteristic of the network in locally, this characteristic can have a huge impact to the whole system. Typically, for example, problem with the congestion is just in one part, in a small part of the city where we can have a problem, but we have a huge impact of the whole system. So we have to consider locally all aspects. So
you have to wrap up in 5 minutes. Sorry about that.
Yeah, I have 5 minutes to.
Yeah.
Okay.
To let you know, because if we want to have a bit of exchange and we're a bit late, so try to go
very fast.
Please.
Yes. So very quickly, the methodology to create this database. We start with three different kind of database. We create a new network that we call the center line. When you have this network, we integrated the information from graph analysis and integrated all information from the characteristic of the street and the characteristic of transportation. And then we have an output, a new network. You know, we can see how we can, what is the result. The starting point is not to start from an existing network. We start from the build-up. So we consider this, that between two buildings, you have a street or a transportation line. So we have I'm not sure what it is. We created that with different geographical processing, and we simplified that. And then we integrated also all information from the transportation, the railway transportation network, in order to know, for example, what is what is the mobility mode that you have. For example, if you have bus stop, or subway stop close to the link. So that is basically what you obtain. We collect all those information in XML format. We prefer to use this format because it's very simple to represent, to create, and is one of the format that is more used to model those to model also geographical information. And basically, the network that you create is undirected, but it's weighted, and it's also geometric, clearly. We integrate a different kind of the information, and the format that we prefer, as I said before, is very easily to integrate in other platform for simulation. And clearly, we have a lot of stuff to do with that. One of them is that we want to create, to formalize this procedure and be completely full access for other researchers in order to create its own database. So that is the first part. How we create our data set. Now is how we can simulate that. I'm a bit late. Yeah, I will try to go quickly. So how we can simulate those transformations? Basically, we start from considering which kind of dynamics we can have in an urban system, and how we can model it also, and we can distinguish two kind of feedback between mobility mode and urban form. From one side, we have a diachronic feedback. That means when we have a change when we have some action from mobility mode, we don't have instantaneously an impact with to the urban form. So people change the way that they interact with each other, but they doesn't interact with the urban form. But after a while, we see that you have some transformation that maybe come from the policymaker, for example. It's not exactly the people that do that, but you have this transformation, and that is a point that we are looking for. From the other side, it's quasi instantaneously that when you have this change in urban form, so we change, for example, the capacity of a part of a street, we see that people change also. We change because we change, for example, we don't have some problem of congestion, for example. So we see this impact. Those two kind of dynamics, we try to model it in a new framework, which is start from this hypothesis. So diachronic impact from one side, the synchronic impact, the feedback from the other side. And basically, the framework we propose is decoupled from two simulators. One of them is an agent-based model in order to model the interaction from a microscopic point of view of people and their moving in a dealing simulation. And on the other side, a dynamic network that is basically represents the transportation network, where the dynamic represents that each part of the network, so each link can transform these characteristics. And we try to simulate the interrelationship. How we can do that? The general framework that we propose is basically start with an input here, where we have the network, and we have the plants. The plants, that means the population that they have to do something during the day. So go to work, go to looking for the children in the school. So this is the plan of the people, and we simulated that in microscopic point of view. We simulated how population behave over a static network. And when we reach an equilibrium of our simulation, we calculated the scoring assigned to each person. The scoring, that means how they actually appreciate the trip that he done. So we assign this appreciation of the people to the network, and at this moment in the first part, we integrated a reinforcement learning algorithm in order to allow the network to choose the best configuration that it should to be in order to improve the scoring of the people. That is so. Thanks the reinforcement learning algorithm, you can maximize this performance. Then we replan the network. We have new configuration of the network, and then we put the output of the new configuration of the network in the simulation, and we test another time in order to we are looking for example, for some kind of equilibrium. So that is the general framework. And in order to conclude this very short presentation, I will say you that we are looking forward to investigate what is the very basically mechanism of behind the transformation of a city in general, but more detailed on transportation network. And we try to investigate that, making some kind of hypothesis. The example is about the dynamics. We created when if we can validate those hypotheses, so we can explain some dynamics historically, but we can also investigate what we can happen in the future. So the goal of this project is also to propose some suggestion to policy maker decision in order to improve the quality of the life of the people. So it is important to investigate it also, and quantitatively measure the characteristic of the network in terms of the robustness of the connectivity or the accessibility also, and evaluate the quality of the urban mobility. So actually, the level of congestion if changes, a huge impact or environmental impact or not this kind of transformation, and so what is the dominant mobility mode that can create some scenario. So thank you so much.
Thank you, Michele. Questions for Michele? For moving on?
Thank you for the presentation. And I would have a question regarding the part where you combine different sources of data regarding the streets. And my question is, do you often encounter contradictions between different sets of data, and how do you solve them? Yeah,
actually, that is the reason that motivated this part. There are a lot of contradictions, a lot of inconsistencies. Those data, it's very difficult to overlap, and then because they come from different sources. And for this reason, the idea is to create a new network from zero, and starting from something that is we are completely sure that is the build-up. So we just consider the build-up, and from them we create a new network. This doesn't start from an existing network. It starts from a new network. Okay. That is our network that we call it the center line, because it actually is in the middle of the building.
So you start with the positions of the building, right?
Exactly.
Okay.
The physical impact of the building, we start from that. We create our network different step of geoprocessing, and then when we created that, we integrated the information from the existing transportation network. Actually, existing network that you can have is not just transportation, energy, what you want. Because here, when you have that, we just find the intersection with the orthogonal line of every kind of the network. And we can say for each part of the network this information.
So I would have a second question regarding on which instances has this method been tested, more particularly in terms of size, and how much time does it take to run this? If it's scalable.
I'm quite confident on about that because the first test that we done is for the whole city of Paris, and to take 20 minutes.
Okay.
So maybe less with a laptop So it's very it's not not required not too much energy and memory.
Okay, thank you.
Yeah.
I have a question. So this is a picture now from the center of Paris.
Yeah.
With the center line. So what happens with this algorithm when you go outside of the city?
Actually, that we found some problem about that. This methodology work very good when you are when we have a very planar city, so we don't have bridge, don't have tunnel, don't have bridge, for example. And also the problem is maybe when we are in the middle of the city, we have for example highway street that cut the city. That is the first step. We developed those, but we don't have too much time to complete that. A methodology to integrate this kind of problem. So the point is to start actually from an existing network. You have to find some compromises in this problem with data. You know, with data every time we have to find compromise. And so the idea is to start with this kind of network, simplify before to implement that, and then we implemented in here. Yeah, but you have some problem about that.
Same question.
Yeah.
Do you handle the topography?
Sorry?
Do you handle the topography?
We doesn't consider we talk about orography, so different. Yeah, we doesn't consider the orography, but it's not a problem actually, because when you consider the build up, the representation of build up of the classical database, consider also this inconsistency of the orography. So yeah, so we can integrate also that. Yeah, actually, we consider some physical constraints. For example, we integrated in this simulation in this database creation. For example, the lake, the bridge, the river. We consider the river Sena to create our database of Paris. Yeah.
Thank you.
Yeah.
Very last one, because you will have to catch up.
It's your time for the next presentation.
Yeah. So when you build up the network from the building, at the end, do you still have the current situations regarding the authorization of certain types of vehicles on certain roads and the only one-way lanes, for example?
Yeah.
Are you able to reproduce that, or it's just a brand new network that is fully?
All those kind of information are integrated in the second step.
Okay.
Because that is the first step, create the center line. The second step is to integrate the old information, and all those information are split to the network. So in this part, in this link, for example, is assigned all the information that from here.
Okay.
So we integrated here in the output. So we say here for each line of the code, we have the information which kind of database we can come from, and actually the feature that you need.
Okay. Thank you very much.
Yeah.
Thank you very much, Michele.
Thanks.
Let's move on.
Yeah. Okay, so
we're running 10 minutes late, but it should be good.
Okay.
Hello, everyone. I am Tarek, a PhD student in the Anthropolis chair theme. I work on agent-based simulation for mobility studies and mobility on demand more in particular. And my work is supervised by Jakob Buchinger, which you know, and Sebastian Hall, which most of you know, who is with us today too. And today I will be talking about some results of agent-based simulation works that we have performed to assess the impact of future mobility systems in the area of Paris-Saclay. So as Tiark talked about before, future mobility systems needs to be assessed, and agent-based simulations are a way to do just that. And without further ado, I will first present the methodologies that we use for our work. So there is a quite well methodology that is established for generating the travel demand for the area of Île-de-France, which aggregates various data sources that are fortunately openly available, which makes the approach completely reproducible by other researchers. So we have data, socioeconomical data regarding numbers of populations and their distributions. We have the mobility behaviors of people from mobility surveys. We have the mobility offer from the publicly available GTFS file from EDFM, for example. And with all of this data, we are able to generate a synthetic population that is activity-based, that contains a list of people, and for each person, a set of activities that are localized both in time and in space on the network. So the video on the right is the visualization of a simulation that is performed using such data. And the simulation framework we use is called MatSim, which I think some of you are familiar. And this tool allows to simulate person by person and vehicle by vehicle the considered people on the given realistic road network. And it allows us to reproduce existing or non-existing mobility systems, for example, public transports or other more elaborate systems like mobility on demand. And it allows us to assess the impact that some changes would have on the people's behavior, for example, or the mode they choose to take, and the travel experience they have throughout the day. And so with this methodology regarding the whole Île-de-France, we are only focused on studying the mobility in a more restricted area, which is the Paris-Saclay area. So to put back into context, Tiark showed the similar map earlier, but you have the whole Île-de-France in red, and this is Paris, and this is Paris-Saclay in blue. It is a gathering of 27 municipalities with more than 300K residents. And as you know, we are in the Plateau de Saclay, which is an emerging innovation center with a lot of universities and research institutes and industries that are currently present and that are arriving. And also on the mobility side, we have two airlines, the RERB and RERC on this area, and one high-speed train station, which is the TGV station at Metz. So with all of this into account, we would like to assess the mobility systems and the mobility behaviors in this area. And to do so, by using this methodology that we have for Île-de-France, we are able to basically cut the Île-de-France simulation just around CPS to simulate a more restricted zone. And this also allows to include the people that do not necessarily live in our study area, but live elsewhere in Île-de-France and travel here for some reason. And this is mostly work. So usually in the literature, you will find studies that are performed on population scales of a certain percentage of the real population, most usually 10%. And this is due to the fact that the more people you take into account, the more time and the more computing resources you will need to run those simulations. So it is written here as a 10% scale. This is what we started with. And then we noticed that on this scale of just simulating Paris-Saclay, we could go to 100%, and this is what we did for our studies. So now that we are able to simulate mobility in the Paris-Saclay area, we would like to simulate not just today's mobility, just today's existing lines, but the future mobility system that will be implemented. And I think many of you already know about the Grand Paris Express, which is the project of 5 metro lines that are in development in the Île-de-France. Well, 4 of them are brand new, from 15 to 18, and one of them is the extension of the line 14. And there is also other tramway lines that are planned for Île-de-France by Île-de-France Mobilité, which are under realization. And the one we are concerned mostly with here is the tramway T12, which links from Massy-Palaiseau all the way south to up until Évry. And for the Grand Paris Express, yeah, it is the yellow one. So this is tramway line 12. And for the Grand Paris Express, we are mostly concerned with line 18, which is the only line from the Grand Paris Express that passes through our study area. So this is a more zoomed in view. And as you can see, we already have RER A and RER C, which goes in 2 ways towards Paris. And the tramway T12 starts in a parallel line to the RER C. And we found it weird, but later we found out that the tramway T12 will replace the RER C on this section, and it will in fact run on the exact same tracks. Yes, this is a view on the future mobility lines, public transport lines that are currently planned or under realization for the area of Paris-Saclay. So we would like to simulate them. So our methodology for that is to generate a synthetic population for Île-de-France, as I presented in the beginning of my presentation. And with this, we obtain a baseline Île-de-France scenario, which uses the latest available data and reproduces the currently existing public transport offer. On top of that, we will add the Grand Paris Express with its 5 lines and also the tramway T12. And this gives us an Île-de-France level scenario with these new lines. We will simulate both of them on the Île-de-France level to have the impact of Grand Paris Express and tramway T12 on the greater area of Île-de-France. So in this way, we might have people that were not passing through CPS that could pass through our study area, giving the new offer. And we do this on a 100% scale. So these computations take around 3 weeks to run for this number of iterations. And so this is not something that we will do all the time on the Île-de-France level. That's why using these simulation results, we will cut it around the study area, the Paris-Saclay, and we will simulate just on the Paris-Saclay area, which is a lot faster to run. And we obtain 2 results, one without the new lines and one with the current lines. And these are the ones that are compared in this presentation. So regarding the simulation results, on the left, you can see the comparison of mode shares that are observed in both simulations with and without Grand Paris Express and tramway T12. We can see that there is not a major difference in the mode shares. We see a slight increase in public transport and a decrease in work and almost unnoticeable decrease in car shares. And this has to do also with the way or the constraint that come when we cut a simulation and we simulate under a restricted area. And we have to consider that a lot of car trips that occur in our study area are people going through the highway that basically goes just through the area and they do not stop in the middle. And these ones will not be allowed to change towards other modes in our simulations. So but what we can observe more in detail here is shares of public transport trips. And we see that the new services, so tramway for the T12 and subway for the Metro Line 18, of course, they gain new passengers. These are new lines, but we can see that most of these new passengers come from bus lines, and there is a slight decrease in the demand for RER B and C. So, of course, we can go in much more details in our analysis. We use a microscopic simulation, and so we can do the analysis line by line and see which lines are impacted. So we can see here that tramway attracts more trips than Metro 18 on the area of Paris-Saclay. And for the bus lines, even if in general we have less bus trips, there are some bus lines that are more impacted than others. And there are exceptions of bus lines that see an increase in number of travelers because they are more connected to these new rail-based systems. And this, of course, should be discussed with decision makers to see what would be the implication of such a decrease in demand for buses on the bus offer itself to have a full feedback loop. And we intend to work on our public institution partners to fully assess these implications. And another interesting point is that even though we have data regarding the future rail-based systems that will be implemented by Saclay, we know nothing or almost nothing regarding future bus lines that will connect to them. And we know these bus lines will be implemented, but we don't know where they will serve or at which frequency, etc. So we had no data for that. But a potential solution to this and a field that is worthy of investigating here is mobility on demand. But before going into depth into that, we can already state that Metro 18 and tramway T12 will attract many travelers, and these will be mostly coming from buses. As example, if you remember Selma, which was introduced this morning, her homework trips between Saclay and Palaiseau, for example, she will not use the 9111 for these trips, but Metro 18 will be a more attractive solution for her. And now we move to the topic of mobility on demand, especially in collaboration with public transport. In the literature, mobility on demand is a service that is made available by a fleet of vehicles, generally considered as autonomous or automated vehicles, that are scattered throughout the network and ready to serve requests as they appear. And these requests are not known in advance, and this fleet needs to be as available as possible to its users. And in the literature, mobility on demand had been studied quite in depth, but a lacking point is the integration of such mobility on demand systems with public transport solutions and the possibility for intermodal trips. So here we investigated the potential of using mobility on demand system as a feeder system towards rail-based public transport, either as an access or an egress mode. And we have worked to implement such a feature in the MATSIM ecosystem. And for that, we take our RER B, RER C, Metro 18 and Tramway 12 lines and make the mobility on demand systems available for people who will take these lines. And we position the vehicles near the stations. And we do it in a manner that stations with a high number of travelers throughout the day will have a greater number of vehicles that are positioned initially alongside them. So, and to implement this system in the MATSIM environment, so here we have the origin of the trip for the person. Here its final destination. So we identify the public transport stations that are nearest to both the origin and the destination. And we introduce access and egress mobility on-demand trips towards the stations. And in between them, it will be a public transport trip as usual. Of course, we have to give some hints to the traveler about the quality of this trip to be able to choose from the other alternatives. So this is the utility that we compute for such trip. We basically aggregate utilities for the different sub-trips regarding mobility on demand and public transport. And we have to mention that the utility computation for mobility on demand is pessimistic regarding the waiting times and the travel times, meaning that we consider that these will be at their maximum possible value given the constraints, but they are somehow optimistic regarding the availability of vehicles. They consider that vehicles will always be available. And this needs to be more elaborated in more future works. So with this taken into account, with this implementation of such a mobility on-demand system, on the mode shares, it's between the orange and the green bars. So the orange is the scenario with just Grand Express and Hamouillouz added, and the green one is with the feeder system on top of that. So here you can think that PT has decreased, but this mode feeder also includes at each time one public transport trip. So in globality, we have more public transport trips. And when we go in details in which kind of trips are served, we see that this mobility on demand fleet that allows people to go to or from public transport stations make these public transport lines more attractive. So we see an increase in RER B and RER C, and also in the newly implemented tramway T12 and Metro 18. And of course, we have less usage of buses. And also here we can go more into detail and see the more detailed impacts on each line. And one thing to notice here is that RER gains a substantial amount of passengers because RER is the main link to Paris. And for example, or maybe most of you here came from Paris by RER, and maybe you struggled with the buses when you arrived and you wished there was some mobility on demand to get here more smoothly. The simulation shows that indeed it becomes more attractive, but again, the buses lose so much trips that we need to have a loop with the decision makers and the public institutions to see what would be the implications. Especially, we need to go further in considering the economic aspect on the operation of such a fleet and whether it is a desirable alternative or not, especially for peak hours. We don't necessarily want mobility on demand to replace buses on peak hours when it's really crowded. So also another thing that we can do is to take a look at the distribution of the origins of mobility on demand trips. Here you can see, so these are the rail-based lines that are concerned by the mobility on demand. And we can see that most of the mobility on demand trips originates nearby the lines, nearby the stations. And this makes sense because they are mainly collaborating with them. But we are also able to identify the areas where people want to access these public transport lines from. And this could be used as a tool to aid the implementation of new bus lines and even study them afterwards in simulation to see at what point does it make sense to replace mobility on demand system on an area by a bus line and see which will be more beneficial both to the users and the operators. So to conclude the study regarding mobility on demand systems, this feeder mobility on demand system, as we call it, make the rail-based public transport lines definitely more attractive. More detailed studies and more feedbacks from public institutions will allow us to really see if to orient our future scenarios and assess the implications for the bus lines more in details. And one implication, for example, of such a system on our personas is Salma, which again has to go on the weekends from Saclay to the south of Palaiseau for her sports sessions. The buses are less frequent on the weekend. So she can maybe take in the future the Metro 18 until Palaiseau and then take a mobility on demand trip towards her final destination, and especially on the way back because it's quite a steep slope, and I know because I live there, so believe me. And yes, it would be an even better alternative than just having the Metro 18. So this is it for my presentation. I hope I didn't exceed my allocated time, and thank you for your attention.
Okay.
Yes, please.
I get a question, Jean-François Robin from Renault. Of course, people will use the new tramway and new means of mobility, but maybe we can consider also that this new mobility means will create new opportunities for users, and maybe it's not just before, after. The comparison is not maybe only a new repetition, but maybe people will take more trips with new ways and new means of mobility. So maybe we have to take that into account also.
Yes, so just to rephrase the question so people could hear it online. So the question was about the impact of these new lines, not only on the number of travelers per line, but also on the number of trips that are being made by people, and the trips themselves or their new potential activities that will be a consequence of that. So indeed, when we did this simulation work, we took the current population as it is. And for our next step, for our immediate next step, we will try to apply the forecasts from INSEE regarding the evolution of population. That could be one first step to do that, but also we could make use of habitat plans that are produced by local authorities to really distribute these new people more precisely around the network. And there are also some data regarding future activity locations, and for example, future malls, etc., could be taken into account to make sure that we are as prospective as we can be. But also when taking also TIAC's work into account by identifying different potential contextual scenarios, we might not just test one possible future, but many of them, and see if which solution or under which configuration our solution performs in a good manner under the spectrum of alternative possible futures. So this is definitely something that needs to be taken into account. And by default, especially in the maritime community, the kind of activities that are performed and the number of activities is not something that is changing throughout the simulation and needs an external loop to have that feedback. Thank you for the question. Yes.
I have a question about the scale of the study area. In order to get the results you got,
yeah,
what is the fleet, the amount of vehicles?
Yeah,
and
so
the capacity,
so
the potential capital cost, and also the vehicle speed.
Okay. So the size of the fleet, we did some fleet sizing. For that, we tested different sizes of the fleet, and this was one of the major reasons that for which we tested only on the Paris-Saclay area, because when we start doing like 10 or 20 simulations, each with a different fleet size, the execution times becomes more important to consider. And we did some fleet sizing, especially to see the rejection rate of the fleet. And we reach our plateau at 1,600 vehicles. Here, the results that are presented are are 4,000 vehicles throughout the entire study area. And the vehicle capacity is 4. And for the vehicle speed, it is the same speed as for the normal vehicle, which is also which could also be discussed. And another thing we noticed is that in contrast with the standards of the literature, the vehicles that we have are quite well used. So we really often have 4 passengers per vehicle at some times. I think this has to do with the fact that we have a feeder system, and when many people arrive at once at one train, from one train, they will highly likely have vehicles at their maximum capacities. Yes, so this is
with 100% population.
Yes, it's with 100% population. So on the Ile-de-France level, when we simulated, it was 11 million people. And when we cut out around our study area, so in this slide, I mentioned that we have more than 300K inhabitants. And but we not only have those ones, we have also people that live elsewhere and that come at some point throughout the day to the study area. And in total, we had a bit more than 700K agents in the simulation.
Did you somehow limit to which stations the DRT can feed the passengers, or is it just to the entire study area, limited to a study area?
So it is the lines, these 2 lines that are in the study area, but only inside the study area. So these 2 new lines plus these the already existing ones. So we have RERB and RERC. So in total, this service was serving 4 lines.
So it didn't put any constraints in like how far the DRT can go?
They just have to be, the stations just have to be inside our study area.
Okay, and then it's like travel time.
Yeah.
Like, could it go to a further one if it would reduce the overall travel time? Or how does it choose the closest?
Yeah, so maybe just go to this slide. So, for example, here, in this zone, in this area, I am sure that everyone here went to this station basically because it's the nearest station. So, also this choice of an access egress station could be elaborated more. Some other techniques could be used to identify this station, but of course, if we are to test all the combinations of access egress stations, it will have a major impact on execution times.
You showed that your scenario presents an increase of the attractiveness of RERB.
Yeah.
And could you envisage that this feeder supports the load balance on the global network to avoid this type of situation? Because I assume that RERB is already quite crowded.
So there are a lot of different opinions on that. There are people who also estimate that the RERB could be used much more than it is, especially by increasing frequency, etc. But yes, this is something that has to be discussed, I believe, with the relevant decision makers who actually know what would be possible or not be possible regarding the RERB. But for the fleet part, we have done the fleet sizing. We are able to identify the correct fleet size to perform well under our particular settings. On the RERB side, it is true that it needs to be taken into account, and what would be the impact of having this much more people inside the RERB?
Something is about the shortest route or shortest trip.
Yeah.
It doesn't take into account the global load.
Yeah, so the load of the RERB is not taken into account, and maybe some metrics like comfort or number of people inside the same train could be taken into account, yes. But this is not something that is currently considered in this current stage of the study. Yes.
Yeah, maybe a last one.
Directly, because I find super interesting as a thought. Do you think that the maximum capacity of RERB and Metro Line 18 is completely at the same time and so on, because in that case it doesn't make much sense, because at both times you have the peak occupation of public transport the same. It doesn't make a big difference. But in the moment where that is not the case, where you, for example, have a stronger peak occupancy during earlier return hours and a higher one later, which I think is quite likely actually, could be quite interesting to say, hey, you get you lose 5 minutes, but therefore you have more space in the
so more detailed analysis could be performed to see how is this increase scattered throughout the day, to see if it's more in peak times or more in
sensitivity analysis.
Also, yes.
Okay, thank you very much.
Thank you very much.
Thank you for being patient.
I have 20 minutes, right?
Yeah.
Okay. I will hurry.
Yeah, don't worry.
You have 20 minutes.
So
this is to next
advance
one, and this is a pointer. This is a pointer. Oh no, there is no pointer. Okay.
Sorry.
Okay. Hello everyone. I'm very glad to be here to present my current work, which is a column generation approach for the electric autonomous dial ride problem. And I'm USG from Saint-Tropez, and this work is collaborated with the Professor Sophie Pack in Linz University, and also with my supervisor Jacob and co-supervisor Nicola. And in my presentation, I will tackle the electric autonomous dial ride problem, which I will explain to you later. And we have proposed an optimization approach with this column generation approach to tackle this problem. And before that, I will tell you a small story to explain what is dial ride problem. This story is based on 4 of my favorite characters in Hunter x Hunter: Killua, Gon, Kurapika, and Leo. And they have passed 3 transportation requests via the platform of Hunter Association, where are shown in the table. So Killua and Gon, they want to be picked up at the origin Kukulu Mountain and be dropped off at the Sky Arena, and they are expected to be picked up during this time window, 8:13 to 9:13, and they want to be dropped off between 11 o'clock and 11:30. And Kurapika, he has a mission to fulfill at New York. So he proposed, so he has passed a transportation request that he wants to travel from Tokyo to New York, and here is his expected time window for being picked up and dropped off. And for Leo, he has a doctor examination in the tomorrow, so he wants to return to his home to prepare for the examination. So he wants to travel from Hunter Association to home, and his expected time window for pickup and drop off is shown in the table. And the Hunter Association have designed a flying boat to fulfill their transportation request, which the physical location for those friends are shown in the slide. So one possible way might be first the flying boat go to pick up Killua and Gon at Kukulu Mountain, because it has they have the tightest time window for being picked up. So go first to pick those 2 boys at Kukulu Mountain, then go to pick up Leo at Hunter Association, then then send Killua and Gon to Sky Arena, which is their destination. Then go to pick up Kurapika at Tokyo and send Kurapika at New York. And then finally, Leo has finally returned to his home. So during this procedure, you may observe that Leo is not very friendly to this plan, because he is the last person to be dropped off, and he shares a long ride with his other friends, and he is the last one to be dropped off. So he has a very long user ride time at the flying boat. How about another plan? Maybe first we still pick up Killua and Gon at Kukulu Mountain, then Leo, then Kurapika, then we send Kurapika to New York, then we send Leo to his home, and finally we drop off Killua and Gon. But this might be a plan that will violate the time window, because Killua and Go, they have a relatively early time window for being dropped off, but they are the last one to be dropped off. So this could not be a possible one for those two boys. So how about we don't have a flying boat, this very efficient traveling mode. We only have our electric cars, which we need to consider the recharging operations during this trip. How about that? How about if we have many cars and have hundreds of customer requests to be fulfilled? How to arrange those cars to serve those customer requests with respect to a lot of constraints. And this is what we will tackle during the presentation. So this is the plan for my presentation. And I will first introduce the electric autonomous direct problem. And a series of transport related problems such as greenhouse gas emission and congestion have appeared, as Flo and Jacob have presented in the morning. And two possible directions have been proposed to address those concerns. One is to use battery electric vehicles. Another is to provide ride sharing services. And dial ride problem, as I presented to you in the small story before. So dial ride problem is defined as to design the minimal cost route plan for a fleet of vehicles to serve customer requests that specify their origins, destinations, and time windows. And however, the research gap is that few studies have been done to investigate the influence of electric vehicles on the dial ride problem. Most of the study considered conventional vehicles, which don't need to consider the operation of recharge on the route. Few studies have been investigated the influence of electric vehicles. And the only one, to the best of my knowledge, is by Bongiovanni, which has proposed an exact method to tackle the electric dial ride problem. And those authors have proposed a branch and cut methods that can solve incidents with up to 5 vehicles and 14 requests optimally. And here is a solution example for the electric autonomous dial ride problem. And in this figure, different colors represent different vehicles. So you may observe from this figure that each vehicle starts from an original depot and serve a set of customer requests and then return to the final depot. And when the vehicles are running out of their energy, so it's necessary for those vehicles to visit the recharging station during their trips, during their services. And so here you can see the recharging station is visited before visiting the next customers. And we need to include this aspect into our study. And before I talked about the electric autonomous direct problem, I would like to first precise what is the characteristic for typical direct problem that are different from the vehicle routing problem. I suppose that you have known what is vehicle routing problem because we have a lot every day. So what is the characteristics of direct problem? First, as I have illustrated, we need to consider the pickup and drop off of the passenger requests. So it's associated to two kind of constraints. That is, we need to consider the drop off node should be visited after the pickup node. And the two nodes for one request should be served by the same vehicle, not by different vehicles. And the second characteristics, which is the most important one, is that we need to consider the service quality. As I illustrated in the small story, Leo is the last one to be sent to his home, and he spent a super long time at the flying boat. So it's not very friendly for him, of course. So we need to maintain a certain level of service quality while serving the customers. And this is often realized by setting a maximum user ride time in the constraint part to maintain a certain level of service quality. And this point will introduce another point, that is, the delay of service begin time. Maybe it's helpful to eliminate some unnecessary waiting time and to improve the service quality. I will precise this point by giving you a small example here. Here is a partial route. The vehicle travels from the depot and then to the first node for the first passenger 1 plus, I assume that each request only associated to 1 passenger. So the passenger 1 is picked up at 1 plus, then vehicle comes to pick up passenger 2 at 2 plus, then drop off passenger 1 at node 1 minus, and then drop off passenger 2 and 2 minus. And here is it's a feasible schedule for vehicle to serve those customers, which precises the service begin time at each node. And we observe that actually the vehicle arrives too early at the node 1 minus, because the time window for 1 minus starts at 155, while vehicle arrived 10 minutes before the 155. Unfortunately, there are 2 passengers on board, so the 2 passengers will wait 10 minutes, both waiting 10 minutes as a vehicle. So in total, 20 minutes waiting time have been generated in this case. However, we can improve the schedule by delaying the service begin time as a node 2 plus from 130 to 140, so that passenger 2, he or she doesn't need to wait at the node 1 minus. So the total user ride time is decreased from 105 to 95. We are saving 10 minutes of waiting time. We are improving our solution by delaying some nodes the service begin. So usually this the solution is the schedule is often being improved by using the 8-step method proposed in the work of Gordo and Laborde. It can improve the solution's feasibility. However, it's just to improve. There is no guarantee to obtain the optimal schedule with the minimal excess user ride time. No guarantee for that. It's just to improve. However, in our study, the electric autonomous direct problem, including the maximal user ride time as a constraint, we consider also a weighted sum objective function value, which including 2 objectives. One is the total travel time for all the vehicles. Another objective is the total excess user ride time for all the users. So we need to optimize the schedule rather than just to improve the feasibility of the schedule. To have a better schedule is not enough. And no method have been designed yet to determine the optimal schedule that has the minimal excess user ride time. So another characteristic is of course the use of electric autonomous vehicles in our network. It will introduce, of course, the detour to recharging station on the route, and we have considered a partial recharging at the recharging station. So here is a trade-off because of the partial recharging. Of course, if the vehicle recharges for a long time, it will visit more nodes after the recharging. Of course, it will extend the driving range. However, the longer recharging time might be conflict with the time window constraint for the succeeding nodes. If there are nodes that has a very strict time window constraint and you recharge for a long time at the recharging station, you might not be able to serve it. So this is a trade-off we need to consider. So we need to tackle this very carefully. And as we considered autonomous vehicle, so no drivers are related to each vehicle. So theoretically, the vehicle can be mannered in a non-stop way. Yeah, there's no restriction on the route duration, and there is a limit of visit to each recharging station. And finally, we have a more specific and artificial constraint in the model, that is the minimal battery level at the end of the route. Why we consider these constraints? Because if we don't consider that, the vehicle can serve as approximately 20 nodes without visiting any recharging station. This means most of our benchmark instance can be solved without visiting any of the recharging station, which is not our interest, because we want to evaluate our performance, the algorithm performance. Well, it has a need to visit the recharging station. We want to analyze their behavior. So we have considered 3 different scenarios as which represented by a ratio of minimal battery level at the end of the route. That means three different scenarios: 10%, 14%, and 17% of the total energy being kept at the end of the route. with the increasing value of this percentage, it means vehicle should keep more and more energy at the end of the route while returning to the depot. That means it's necessary for those vehicles to visit the recharging station before returning to the depot. And it will allow us to analyze the routing results according to those three different scenarios: low energy restriction, medium energy restriction, and high energy restriction. And here is the objective function for the weighted sum formulation. And this is the decision variables. And for the consequence, here is listed here. And we are tackling actually with the static version of data-right problem. So all the requests we are known in advance. We are knowing all the requests in advance. The dynamic version that I will tackle in the future in my thesis is that the request can be updated during the day, and the vehicle has the right to reject or accept the new request generated by the customers. But now in our study, this study, we're tackling with the static one. So all the requests are known in advance. And we have formulated the electric autonomous data-right problem into a set covering problem, which is also called master problem. And the set covering problem, we have the decision variable is called y omega. It's a binary decision variable, and the big omega here is denote the set of all feasible routes. So with the increasing number of customer requests, this will grow exponentially. So it's impossible to solve directly this version. And we have converted to a relaxed version of the master problem, which is a continuous restricted master problem, a subset of omega. And we use the method of column generation to add columns to omega prime, the subset of omega, and solve again the continuous restricted master problem. And I will precise the methodology in the next slide.
Maybe quickly, if
you
can, to leave room for questions.
Okay.
Maybe
wrap
up in a few minutes.
Okay. So we have proposed a column generation to solve this problem, and the continuous restricted master problem is shown in the left-hand side, and the pricing subproblem is formulated with the dual variables associated to each of the constraints in the continuous RMP, and the objective function, and the pricing subproblem need to satisfy a series of constraints. And the column generation is described as an iteratively solving of continuous RMP and the pricing subproblem. The continuous RMP will update with the pricing subproblem the renewed dual variables to formulate the objective functions. And the pricing subproblem is to find the negative reduce the cost columns and add it to the omega prime. And this problem will be solved again to update the dual variables associated to each constraint. And this will be iteratively solving until no negative columns can be found. And we have proposed a leveling algorithm to solve the subproblem, because actually the efficiency of solving subproblem is the key factor that impacts the overall algorithm performance. And the labeling algorithm, the general idea of the labeling algorithm is that we extend the partial path from the original depot until the destination depot, node by node. So for example, we send node by node, and on each node, a label is associated with each node. And in each label, there are several resource attributes included in each label. And while extending the label and the partial path, we need to check the feasibility for the extension to make sure that each extension is feasible until we reach the final depot. And we return all the routes with negative reduced cost. And during this extension procedure, the resource extension function is used to update the level of the new node. And we can use a dominance rule to accelerate this algorithm. For example, here there are three partial routes. Both of those three partial routes end as the node I. If the partial routes red one dominates the two one, so we don't need to consider those two. We only need to extend this one, because if this one is better than the two, you can replace this plan. And so we only need to consider the red partial root. And now I will quickly summarize the computational results. We have examined our algorithm on 3 instance sets, and the first 2 instance sets are based on the study of Bongiovanni in 2019, which is initially introduced by Bongiovanni. The first one is based on the it's based on typical direct problem, but supplemented with the character of recharging station. And the second one is based on the real-world ride-sharing dataset of Uber technology. And the maximal instances contains in the 2 benchmark set is up to 5 vehicles and 15 requests. And we have constructed ourselves a larger instance set with up to 8 vehicles and 96 requests, which is called type R instance. The first one is type A, the second one is type U, and the last one is type R. And for each instance, we have tested 10%, 14%, 17%, those 3 scenarios on each of the data set. And here is the results for type A instances under 10% of the energy being kept at the end of the route. And here are the results. And we summarize with our column generation algorithm, we can solve 12 out of 14 instances as a root node without branching, without calling any branching. And we improve the lower bound that's reported by Bongiovanni by 0.7%. Because in this case, actually most of the instances solved optimally also by Bongiovanni. So their lower bound equal to the objective value. There is actually no space for improvement of the lower bound. But for those instances that doesn't prove optimality in the work of Bongiovanni, we can improve the lower bound of those instances by up to 5%. And the computational time has decreased a lot. And here's the result for 14% case, where we also solved most of the instances optimally as a root node, and we have reported 4 new optimal solutions identified. But here we find an exceptional occasion, because we found actually we prove optimality for this instance. The optimal value is 347, while the optimal value reported by Bongiovanni is 348, which is not equal and exceeds the tolerance gap. And we actually find there a wrong parameter using in their study, which they actually cut off some optimal values for some instances. And our approach finds the real optimal value for those instances. And just something to implement. And for the most difficult cases, with our column generation, we are able to solve 5 out of 40 instances optimally as a root node, and we report 7 new best solutions, and we've improved the lower bound and also with the lower computational time. And here is for Uber instances, similar findings have been observed, and our algorithm can tackle the large instance set, while the literature method cannot. This is a new result reported by our algorithm. And here is some summary for the performance of the algorithm. And I will move directly into the conclusion. So we have proposed an efficient algorithm to tackle the EA-DARP, and we have proved a significant improvement on the lower bound quality and the solution quality. And the column generation algorithm is able to handle a larger scale instances. And the future work will consist first, extend our labeling column generation to the related topics such as electric pickup and delivery problem with time window. And also another context is to consider a multiple objective optimization. And another interesting direction, maybe we can consider a dynamic version of diorite problem, because we are now tackling with the static one, and we can consider to handle the dynamic one with the request can be added, renewed. So here is a reference. Thanks for your attention. If you have any questions, I would be very happy to answer this.
questions? I can start with one.
Yeah.
Small question for you. You talked about some constraints.
Yeah.
Can you imagine a kind of constraint when you have a constraint on the energy supply or the electricity supply for an area, because we might not be able to provide for electricity as much as we want? So is it possible?
Yeah, you mean have some uncertainties in the energy supply?
It could be something like that, or maybe saying for 10 or 15 charging points in the neighborhood. Is it maybe there's a maximum you can deliver a day, possibly?
Maybe.
Kilowatts?
Maybe I think it would be it would be possible to include this aspect into our study. For example, we can consider certain properties that this charging station is not open for the vehicles, for example, to add something like that to say if we can still solve the instance under considering this kind of uncertainties, if I understand correctly.
Well, I think it would be to monitor the energy, maybe.
Yes, maybe. Maybe. And actually, we have considered in our study as like a specific constraints for the recharging station, because this constraint is that we have a limitation of visit for each recharging station.
Okay,
yeah. It's a little bit similar to the, for example,
it would be another way.
It would be another way.
Thank you very much for the narration. It was
okay.
nice.
Well, it's yes.
Can I add something to this? I think so. There is some problems or descriptions where there is a specific focus on the organization of the recharging, and where there is also consideration of several recharging spots at each recharging station. So how many vehicles you can charge at the same time. And there is also then algorithms for scheduling the recharging at each station. So which vehicle can recharge how much energy at which outlet. However, these are problems by themselves that are very hard. And if we combine them with the routing problems, the problems get even harder. So depending on the overall problem setting, it will then become, I would say, quite challenging to solve it, especially in an optimal way as you showed it here. It could be done then easier with some heuristics, similar to the work you did in her first paper, for example, or even with some more dynamic rules for assigning the vehicles and the charging station.
Thank you. Any other questions before moving to the last one? No question?
Yeah, already asked many questions on Wednesday.
I have a question.
Yeah.
So just I didn't understand what the justification of saying I want to be at the end at 70% of it. So a part of making the problem more interesting, but in reality,
Yes. Actually, this conference is introduced initially in the work of Giovanni, that because without considering any of the constraints at the end of the route, most of the instances can be solved without any concerns, without visiting any of the recharging stations.
Yeah, but what is the time horizon?
Time horizon, so
I think it's one working day, and for one of these things is 1 day. And the idea of having 70% when coming back in the evening is that maybe the person is not coming back to the central depot of the company, but maybe parking the car in his, or it's autonomous vehicles, so it's like different. But if the car is not parked, for example, at a spot where you can recharge, it must be able to have some more energy on the next day. So it can be of because of operational constraints, actually. So that's the idea. Another argument for the 10% is, for example, that you never want to make the car completely empty, right? But this also, you could just let always this 10% in the battery and don't consider it at all, right? The 70% allows you to go down at some point in the day way below, but then at the end of the day, you have to get back to a certain level.
Yeah, this
so
is
that
just...
the car is ready for more.
But you can also assume that the morning peak hour.
Exactly. Or you can also say, for example, that the car, that the day ends, it goes from 9 to 6, and then the car has to be again on the road after 28, and maybe it has to have some battery, and it should not recharge in this between 6 and 8 or whatever. I mean, there can be many reasons. But of course, here it's an artificial,
artificial
to see what happens with different charging levels and so on. See how the algorithm reacts, how the results look like.
Thank you very much, Hugh. Thank you for your questions. Thank you.
We have one chair, you can share.
But it's Flo is the chair holder,
yes.
right?
So you get the chair.
I don't have a chair, but I don't need it because I'm not talking.
Tu avais des sacs aussi? Ok, je vais la mettre.
So maybe in the meantime, I take the opportunity to congratulate you all for the very interesting works. I think very, very rich, very dense, and yes. So it's quite a pleasure to, yes, even for me. Perhaps I was supposed to be more involved in these activities before, but I would say that maybe within ERT Systemics, we should get, and that's part of my role, also a better connection to this, to all these works. So yes, the idea was to wrap up before the final wrap up. I don't know if do we need a slide?
Yeah, we have a
very
slide.
super complex slide.
Okay.
Good sport.
So just
Okay, I think we can start with this nice background.
All right, so yes, just have a couple questions to you, Flor, and yes, once again, congratulations to both of you also for these works. We noticed today that all these Anthropolis members displayed and provide a very large diversity of activities and work, and this is probably we have seen a challenge to handle this multidisciplinary approach. So how do you handle this all these skills coming from different universes to ensure that it converges or it generates coherency at the end of the day?
Can I start?
Yeah.
I think that's a very hard one, right? Not the question, but doing it, right? Or not. It depends on the people you are working with. So on the one hand, ourselves, Flor and myself, are coming from some different areas and disciplines. So that's the first thing of how to handle it, because already two of us are covering some different parts, and we are well working together. So that's also, I think, very important. And then it's about the exchange in the team. So we saw this already in the first season of the chair, where we had students, Wail, Aboud, and Reza, and they were also exchanging a lot, and they were working together. And at some point, quite at the end of the season of the chair, and everyone was doing their work, what they were talking about, suddenly they came to us we said, actually, we want to make a paper, the three of us together, where we do something where all fits together. And it somehow emerged out of our discussion and so on that they had this need to do something together. And this was some really nice or cool surprise for both of us, I think. And now in the second one, it's also, again, using meetings, using exchanges, discussions, trying to understand each other, to also listen to each other, because it's also very difficult. We are talking different languages, right? You hear about dual variables being exchanged, and then on the other hand, you hear about, I don't know, the needs of a population that has some behavior or whatever, right? So we need to listen to each other, to talk to each other, try to understand to each other, and to translate somehow between these cultures and see how we then can make emerge also things together. And again, we have several now, I would say, directions, different members, between Sebastian and Michele, between Tarek and Tiag, between Mariana and also Tiag and others. So we have many exchanges and possibilities of doing things, right? So maybe, Frau, you want also to add something to this.
Yes, for this second chair, we have the opportunity to work with industrial engineering design, but also urban design and sociology. We integrated, and so more the computer science part. So it's true that it's challenging. It's really nice and pleasant to get into that. And if I come back to this sustainability part on infrastructures I mentioned this morning, we had a lot of discussions, and in fact, it appears we have a lot of ways of modeling socio-technical subjects, and the idea is not to aggregate everything in a huge model. In the end, we say, well, this modeling or this viewpoint is really good to bring knowledge on these aspects, and the other one is good on that. So, but there was this temptation to integrate everything. And in the end, I think that's not really what we are doing, but we are well aware of what the neighbor is doing in his field. So, yeah.
Great. I think it's very, assume it's very, very coherent, and there's a really consistent and nice storytelling throughout the day and the works. But it's not a bad. Now, all the from my perspective, all these works and these activities are very urban. We are talking about services, and we are talking about shared modes and everything. And do you think you can expand these works or part of these works in more rural areas where the status of the individual vehicle is quite different from what we what had been tackled or displayed today?
Question?
I think partly yes. Some things absolutely make sense and can be easily extended, right? For example, youth work, her algorithm will work in a rural setting or in an urban setting. Other things like, for example, walking in mobility as a service does not make sense if everything is like 20 kilometers away. If your next neighbor or whatever is, then okay, you can walk 20 kilometers, but it's not really a lot. It's not so relevant anymore in a rural setting, right? On the other hand, we are not only looking at the rural setting. I mean, that's urban setting, that's the main topic, but we are also looking at more suburban or peripheral or even rural settings in the works with Julia. So where we are getting more and more interested also in topics. However, it's much harder to say we get rid of the car completely, as it is, for example, if you live in inner city Paris. Right?
Yeah, it's true that I think we're heading towards tackling the problems of less dense areas with the PhD of Julia. So that's a bit what's on the tracks, I guess, because we started with his internship working on battery electric vehicle mobility on highways, and then we were questioning ourselves regarding the eco-design part on what is the relevance of the battery electric vehicle in urban areas, or is it more relevant in other settings? So that's how it started. And I think it's really important, as you mentioned this morning. That's an important challenge, and it's true. We can work much more.
Yeah, I think this is valid for the whole systemics or even yes, the whole research and development world to broaden the scope. Yes, apart from all the urban areas.
And there are very urban and rural areas on the plastic sector.
Yes, perhaps. Yeah, I mentioned rural areas, but less dense areas is probably a better wording. Yes, and
last one.
Last question. Quick.
Let's go.
Did you, from your perspective as researchers and shareholder, do you have one in your head, one single driver that could leverage the innovation of mobility in a mid-term perspective? On which driver would you bet for the next years?
So for me, after what happened in the last 2 years and what happens today, it's on the one hand an easy question because it's throwing a virus, right? Make people work from home a lot, throw in an energy crisis, make fuel and electricity extremely expensive, right? And people will start using their bicycles and walk, right? So that's, I mean, on this side, it's easy, right? But on the other hand, what we see in reality, what we see in areas where it's not so easy to bicycle, then you have to also make the things change. But for example, here again, it's a very Parisian view of things, but how Paris inner city changed in the last 2 years is just crazy. Yeah. I mean, it's you have the feeling that soon you will have built bike lanes, protected bike lanes everywhere, right? And you will soon be able to bicycle with your 7-year-old child through the whole of the city.
Yeah, we will live in Holland.
Exactly. I mean, it's almost a feeling like this, right? That there is but that's not the whole country. And for this, it's I think I don't see one thing, but still also for the rest of the country, this I would say economic and pressure will be the major driver.
For the drivers, I don't know magic solutions. Of course, we have to rely on technological solutions, but bearing in mind that I'm doing sustainable design, of course, we have to focus on solutions that are absolutely sober in as many ways as possible. And I would focus on solutions that related to way of life and changing behaviors, because that's a very important driver for transport. And sometimes it's a bit underestimated as well, even in projections from the IPCC and others. So I would focus more on that, and also take into account the notion of rebound effects we mentioned a bit. Saying, trying to not anticipate, but just have a look at, try to imagine the indirect effects. So that's not a solution, it's more questioning as we do in research.
Okay, thank you both. Thank you all again. I will just one last word. I really appreciated also talking for all the people watching us from all over the globe. But I think all the works and results are very well, very concrete and very connected and very impact oriented. And that's what we used to do here, and it's appreciated a lot. Thanks.
Thank you very much, Jan. So just for a moment, I have a slide, but it's not
word.
Yeah.
So I would say just one word.
Yeah,
that
that's the one.
I thank very much the whole team and for their work and their presentations that I appreciate a lot. So thanks for that. That's what I want to say.
Thank you. Thank you, Yann. I would like to finish in French. Je peux finir en français. C'est dommage que Gaston n'est plus là.
Mais il est là, il est en ligne.
Ah, il va être content.
Oui, il était, mais
Okay. So just a few words. Thank you for attending online to this colloquium, and I will finish a final word in French. Merci beaucoup, Yann, à toi. Donc, chef de projet à IRT Systemics, qui est maintenant mon bras droit sur la gestion de la chaire pour l'année qui vient. Donc, je suis très contente de faire avec toi. Et puis, merci à Jacob pour ces plus de 6 années qu'on a passées ensemble. Ça a été une très belle collaboration. Je crois qu'on peut être très fiers de tout ce qui s'est fait aujourd'hui et puis de tous nos résultats. Donc, je souhaite qu'on continue à travailler ensemble et puis plein de bonnes choses pour le début de tes autres activités. Et de toute façon, tu suivras de près toute la suite. Donc, voilà, c'est ça.
Et je reste aussi avec les doctorants.
Voilà, donc c'est une belle continuité. J'ai pris mes petites notes parce qu'en général, j'ai peur d'oublier des gens. Donc, je voulais remercier nos partenaires industriels, sans qui tous ces travaux ne seraient pas possibles. Donc, merci à vous d'être présents sur place, à distance, et puis de travailler avec nous et de nous accompagner dans ce travail. Merci à IRT Systemics et à Centrale Supélec, qui sont nos hôtes pour la chaire. Je ne vais pas du tout oublier l'équipe de la chaire. Je dis l'équipe étendue, parce que vous avez vu avec tous nos présentateurs, on a une grande équipe. Et avec tout son enthousiasme et son dynamisme et vraiment plein de belles contributions. Donc, merci beaucoup pour ça. C'est un vrai plaisir et plaisir à continuer avec vous. Alors donc, tout le monde, Tarek, Mariana, Tiark, Widad, Yu, Michele, Julien, sans oublier Sylvie, qui est notre mise à disposition et qui nous avons plaisir à collaborer aussi dans l'équipe. Réciproque. Merci aux personnes qui sont venues nous écouter aujourd'hui en ligne et puis sur place. Et Sébastien aussi, tout à fait. Excuse-moi. Merci Sébastien aussi pour ta présence et puis ton soutien et plus que le soutien, le travail collaboratif qu'on mène ensemble. Et merci à notre designer graphique, René Rodriguez, qui nous a fait le plaisir d'illustrer certaines de nos cas d'études juste pour l'occasion. Et je crois que je n'ai plus rien fait. Donc, c'est bien. Donc, la séance est levée. Est-ce que... Waouh, on est trop bien.
Oh, super.
Merci. Ils ne sont pas ultimement pressés. Je pense qu'il y a une petite pause, c'est ça?
Il reste 2-3 broches.
Ouais, oui, non, il reste quelques petits gâteaux, il reste des rafraîchissements. Si vous voulez discuter un tout petit peu avant de repartir.
Il y a du café, du thé, des
ouais, voilà. Il y a une petite pause, si vous voulez. Merci beaucoup tout le monde.
Merci. Merci.
Merci.
Et tu ne nous as pas rendez-vous l'année prochaine.
Mais oui, rendez-vous l'année prochaine pour le dernier cours, bien sûr. Je ne m'étais pas encore projetée.
Qui ne se fera qu'en présentiel.
Qu'en présentiel. Exactement.
Ok.